Namaskara. In this session, we are going to look at a very nice idea, a clever technique to design divide and conquer algorithm in a more efficient way. We are going to suggest certain improvements which will allow us to design divide and conquer algorithm with better efficiency. Okay? The technique is called more for less. Okay? So, let us consider the following problem. You are given an array A of integers. You are given an array of n integers. A subarray is defined by a pair of indices I and j. Okay? So, A, I, j is a subarray from I to j, I and j included. Okay? This is a subarray. So, subarray sum okay, Sij is defined to be sigma of Ak k going from I to j. Add all the numbers from Ai to Aj, Ai plus 1, Ai plus 2. So, here we assume that I is obviously less than or equal to j, only then a segment is meaningful, and subarray and subarray sum is given by. So, you can choose a pair of indices I and j with I less than or equal to j. So, choose one less than or equal to I less than or equal to j less than or equal to n, and you have Sij defined for it. The subarray sum is defined for it. Okay? And there are only n choose 2 plus n for I equal to j. When I not equal to j, you can choose 2 numbers, n choose 2. So, how many subarray sums are there? You have n choose 2 plus n, that is n times n plus. So many subarrays are there, and each subarray has a sum, and you are interested in finding the maximum subarray sum. So, there are n times n plus 1 by 2 subarrays are there. Each subarray has a sum associated with it, and you want the maximum of all these numbers. Okay? That is the problem. It is a very simple, clear and well defined problem. And there are very simple ways in which the maximum subarray sum can be computed in order n square time. A very simple way. We are going to compute all the subarray sums and then find the maximum. Okay? So, how do you find all the subarray sum? Per subarray sum, we will use one operation. Okay? So, if you visualize the subarray sums arranged in a matrix, it is going to form an upper triangular matrix. So, 1 1 2 2 3 3 n n. So, 1 2 2 3 1 3. So, like this you have 1 n, 2 n, 3 n. So, you can see that this each entry is a subarray sum. What is for example, what do you mean by 3 7? It is or 3 comma 7, it means subarray sum A3 plus A4 plus A5 plus A6 plus A7. 3 3 means simply A3. 3 7 means from 3 to 7, all this subarray sum. Okay. So S 3 7 is sum of all these numbers. So I am going to find the subarray sums in this row wise. So S11, S12, S1n, then S22, S2n, S33, S3n, and finally Snn. I am going to compute row wise. When I compute row wise per subarray sum, I have to perform only one addition. For example, if I have S16, how do I use it to compute S17? It is simple. S16 plus A7 is S17. Therefore, keep adding one number and get the next subarray sum. So start from S11, which is A1, S12 is A1 plus A2. So how do you get it? From A1 add A2. The next one is A1 plus A2 plus A3. So add one more and get A1 plus A2 plus A3. So in this way, each subarray sum can be computed by performing one addition operation. I have the previous value, add one more value and get the next subarray sum. So starting from the diagonal values, which does not require any computation, because what is SII? SII is simply AI, only a single value, no addition is required. So the diagonal sums do not require any calculations. Starting from there, go row wise, keep adding one element each and get the subarray sums in that row. Therefore, this is going to be an order n square algorithm, very simple. And as and when you find a subarray sum, update the maximum subarray sum. Okay. So very simple and direct. And there are other ways to find the subarray sums in constant time with one operation, and that is called the pre-processing technique. It is a very interesting technique. Okay. Consider x1 equal to a1, x2 equal to a1 plus a2. In this way, xi equals a1 plus a2 plus ai. Finally, xn is a1 all the way up to an. Suppose you compute these values, very easy to compute. From xi, get the next value xi plus 1 by one more addition. So keep adding one number to the previous one and get x1, x2, xn generated. A simple one pass computation. If you have this, what is subarray sum Sij? Sij is nothing but xj minus xi minus 1. This is Sij, because xj is a1 to aj added, you want only from I to j, so you subtract 1 to I minus 1, the sum. So when you subtract, you get Sij. Therefore, each Sij can be computed with one operation. Compute Sijs one after another, and as and when you compute, update the max, Therefore, you can have the Sijs and max updating all done in order n square. This is another method. Okay. But in this method also, per Sij you are doing only one operation. Okay. So, all these things are n square. Here is a divide and conquer algorithm. Immediately it is going to give you an n log n solution. Okay. The divide and conquer algorithm, and that is going to give n log n solution. So, let us call maximum subarray sum, maximum subarray sum. Instead of writing every m s, let us write like this, and so MSS, okay, maximum subarray sum is going to take a 1 dot dot n as an input, and perhaps the number of items also it can take as an input, but in general that is not necessary, and it is going to output the maximum subarray sum. Okay. This is going to, in fact we can also output the corresponding subarray by providing those two indices which gives that sum. It is a very minor extension. Okay. So, we will focus on the maximum subarray sum. Okay. And you can call that maximum subarray sum as M. Okay. M stands for maximum subarray sum. Okay. Now, our divide and conquer algorithm is going to split when the array size is more than 1. If the array size is 1, if n equal to 1, well, when there is only one element, that is the array, that is the subarray, that is the only subarray, and that is the maximum subarray, and that is the maximum value as well. Therefore, if n equal to 1, m equal to a1 and return m. If n is more than 1, okay, if n is more than 1, else let q equal to floor n by 2, you are going to find maximum subarray sum of a 1 dot dot q and call that value m1, then recursively call maximum subarray sum on the array a q plus 1 dot dot n, call this as m2. So, what is that you have found so far? You have found so far this is 1 and q, this is q plus 1 and n, the maximum subarray sum m1 for this, m2 for this. Okay. This is what you have found so far. Recursively you have solved for the first half, you have solved for the second half. But the maximum subarray physically, it may be located in the first half, it may be in the second half, or it may overlap. In other words, your maximum subarray may be of this form. Okay. It is starting in the first half and ending in the second half. It is not entirely in the first half nor entirely in the second half. If it is entirely in the first half, M1 would identify that. If it is entirely in the second half, it will be identified by M2, but then you do not know where that maximum subarray is physically located. It could be a overlapping subarray, okay, overlapping subarray. And in the calculation of M1 and M2, we have never considered the overlapping subarrays. So M is a maximum among the subarrays in A1 to AQ, M2 is maximum among the subarrays in AQ plus 1 to N, but we have never even considered the overlapping subarrays. Okay, we have never considered the overlapping subarrays. So we have to find out the maximum of overlapping subarrays. So we call that as overlapping max. Overlapping max. This is overlapping subarray max. So what is our final answer? M equal to maximum of M1, M2 and overlapping max. Because a subarray can be either in M first half or in second half, or it may overlap. In each category we have got the maximum. So the overall maximum will be subarray sum maximum, and that is what we want. This M is nothing but maximum of these three numbers. But I have M1 and M2, how do I get this overlapping max? Okay. So if you look into the property of the overlapping max, okay, it has got an interesting structural property. So this is the array, this is Q, the split point. How will the maximum overlap subarray will look like? Let us say the overlapping subarray is from P to R. This that is APR is maximum overlapping subarray. Let us say because this is maximum, if you add any of these values further, you are going to have smaller value or equal value. If you could get something larger, then that would define the boundary or the left end point of the maximum subarray. That P and R is defining the maximum subarray. By the way, the numbers can be positive, negative, 0, multiple copies, it is an arbitrary array of integers. Okay. So in fact after P, if you have only negative numbers, adding them will make it smaller and smaller. Therefore you can see that this is maximum, means anything else you add you are going to get smaller value. Similarly anything you add you are going to get smaller value. In other words, this portion, okay, which is in the second half, let us say this is Q plus 1. These values, this sum Q plus 1 to R must be a maximum among all these sum of the type A Q plus 1, A Q plus 1 plus a q plus 2, a q plus 1 plus a q plus 2 plus a q plus 3 and so on. Okay. These kind of sums, okay, are called prefix sum. Okay. These kind of sums are called prefix sum, and this R is maximum. If this is not maximum and somewhere larger is available, I can extend to that point and get larger value. That I am getting the larger value at R means all other extensions are going to have a smaller value, maybe equal, but definitely smaller than or equal to values. Therefore, we call this as prefix sum. So, what is a prefix sum for an array? The prefix sum for an array, okay, prefix sum for an array A I dot j. What are the prefix sums? Prefix sums are the following numbers: ai plus ai plus 1, ai plus ai plus 1 plus ai plus 2 and ai plus ai plus 1 plus aj. All these numbers are prefix sum. Prefix sum max, okay, or prefix max is an index R. Let us say among all these numbers somewhere you are getting the max, somewhere you are getting the max, and that index defines the prefix max index, and that is the prefix max value. Okay. So, you can call that as prefix max ij. This is prefix max in the array defined by array aj, prefix max in defined by a I to j. For example, I have a big array, but I am giving you only the following element. Let us say the third element is -6, the fourth element is 8, fifth element is 0, sixth element is -10, seventh element is 11, 12th element is 26, 13th element is -3, 14th -5, 15th, sorry, 7th, my apologies. 8, 9, 10, 11 is 2. What are the prefix sums? -6, add the next number 2, add the next number 0, add the next number -8, add the next number -8 plus 7 3 plus 26 29, -3 26, -5 21, 2 23. This is where the maximum is. All prefix sum, and this is that R, index R. This is the index R where the maximum has occurred. When there are several maximum, you can take any one of them, it does not matter. In this case there is only one maximum, you are considering that as the maximum. This is called the prefix sums, and among the prefix sum it will be the max. Now this part must be prefix max. This part must be prefix max, because anything else will make it smaller. So if I add something, I am going to get only a smaller subarray. That is the reason why this R can be found by computing the prefix sums and the maximum among the prefix sum. Maximum among the prefix sum. Similarly, this part is called the suffix sum and suffix max. Suffix max means, what are the suffix sums? Suffix sums start from the other end. Suffix max or SM ij. How do you find? You have the array A I dot dot j. What are the suffix sums? It comes from the other end, aj. Aj plus aj minus 1, aj plus aj minus 1 plus aj minus 2. All these numbers like this, you have numbers and get the maximum on this numbers, and that will be suffix max. Okay? That will be suffix max. Therefore, how to find the prefix max and suffix max? Compute all these values and find the maximum. That will be suffix max. Similarly, for prefix max, we have worked out an example. For the same array, I can get the suffix max. Alright? We can get the suffix max. Start from the other end. Okay? Or I can work out some other example. Let us not confuse that. Okay. 5, 3, minus 10, minus 8, 6, 12, minus 2, 9, 8. What are the suffix sums? 8, 8 plus 9, 17, 17 minus 12, 15, 15 plus 27, 27 and 6, 33, 33 minus 8, 33 minus, let us say this is 23, okay. 33 minus 8 will be 25, 25 minus 10 will be 15, 15 plus 23 is 38, 38, okay, let us say minus 5, 38 minus 5 is 33. Therefore, this is where okay, this is suffix max. From the other end, you have computed what is known as partial sums, and you have figured out that this is where the suffix max is found, and that is the suffix max value. Okay? So, we are going to use the notation suffix max and prefix max, SM and PM, and give a range of indices, which means in that subarray the suffix max value and prefix max value are given by SM, IJ, and clearly the complexity of suffix max or prefix max is the size of the array, because you have to compute all these partial sum. You have to compute these partial sums and find the maximum. So, partial sum is incrementally found. Start with AJ, then one more addition you get this partial sum, one more addition you get the another partial sum. In this way, you will keep building the partial sums and figure out where the maximum is. Therefore, it is proportional to the size of the subarray j minus I, right. It is proportional to j minus I. So, for our divide and conquer algorithm, all I have to do here is to find the overlapping max. Look at this picture. The overlapping max, if you want to find, you have to add the suffix max, overlapping max equal to suffix max of 1 to q in this part, whatever is the maximum, and prefix max of q plus 1 to n. In this part, from q plus 1 to n, whatever is the maximum, suppose you have achieved the maximum here. So, from q plus 1 to the right, you have a maximum right end point. From q, you kept moving to the left and the maximum left end point. When you put together, you are going to have an overlapping interval, and that overlapping interval sum, that will be the max. So, overlapping max is suffix max 1q, prefix max q plus 1n. You can compute suffix max 1q, prefix max qn as I indicated here. Therefore, I will write now the pseudocode for the algorithm. We will write like this: maximum subarray sum of a1 dot dot n, and it is the output is m, okay, if n equal to 1, then a1 equal to m, or m equal to m, that is what the value we return, we want to return. Return m, else let q equal to the split point floor n by 2, okay, maximum subarray sum of a1 dot dot q, and you call it as m1, maximum subarray sum of a q plus 1 dot dot n, and call it as m2. Now, find suffix max, compute suffix max for the array 1 q, compute prefix max for the part q plus 1 to n, compute suffix max, okay, sum is the notation, let us write like compute the suffix max sm for sm1 dot dot q, compute prefix max pm compute prefix max pm for pm q plus 1 dot dot n, overlapping max is suffix max plus prefix max, and m equal to maximum of m1, m2 and overlapping max m1, m2 and overlapping max, and return m. So, you can see that this is the combining cost. All these things are in the combining cost. So, what is the combining cost? This is a recursive call, this is the combining cost. You have to compute from 1 to q all the numbers and find the maximum, and that is going to take q steps. Q plus 1 to n minus q elements are there. Again you have to compute the partial sum and find the max, n minus q. So, q plus n minus q is n, q plus n minus q is n, then 1 or 2. So, it is order n, exactly it is n plus 2, but we will write it as order n. Therefore, if Tn denotes the number of operations or additions, right? That is the only thing, the additions done by the algorithm, then T of n equals T of floor n by 2, this is to compute m1, T of seal n by 2, this is to compute m2, and then this is order n, this is order n combining cost, and T of 1 equals 0. When there is only one item, no addition, nothing is done, T of 1 is 0. So, this recurrence equation has a solution T of n as order n log n. It is like merge sort recurrence, okay? It is like a merge sort recurrence. Therefore, the complexity is order n log n. So, I have a divide and conquer algorithm that is n log n. Now, the magical step, we are going to suggest a way to improve this. That will also be a divide and conquer algorithm, but that will have complexity order n. In other words, we are going to reduce the combining cost to order 1. We will see the magical step and the clever move that we have to do in our next session. Thank you.